Hey, welcome back, everybody. I hope you're doing fine. I wanted to give you some kind of small messages before we begin. You probably received the email with the update from yesterday and plans for today and tomorrow. If you go to the GitHub address of the course and you click on the link which you have here on Nuclear Talent. So the plan today is to cover an introduction to neural networks. And the aim is to demystify what a neural network is, and then to also give you a kind of an example on how you can build your own code for a neural network. And the reason why we're going to do that is that many of the ingredients which you will meet here are things which will appear again in next week when we're going to look at classification problems using convolutional neural networks, or when we're going to use recurrent neural networks, or more advanced deep learning methods. Some of the basic ingredients, like a gradient descent approach, which we discussed yesterday, is something which you will see appearing again and again when we now look at the deep learning methods. So deep learning is just another word for saying that you have a network with many, many hidden layers. And at the heart of these neural networks, there is a very simple algorithm. And you will be surprised to see how simple it is. It's called the backpropagation algorithm. And that is essentially something which you did back in kindergarten. I mean, the chain rule is an application of the chain rule. Nothing but that. And the algorithm is actually very simple. And when you've done that, what you end up with is essentially, from a mathematical and computational point of view, is just a set of matrix vector and matrix multiplications. And these have to be done efficiently, combined with a gradient descent algorithm, which then finds the optimal values. Now, going a little bit ahead, so tomorrow we are back to physics. And the kind of physics we are going to look at are beta decay experiments. So we are going to have an intermediate step in the exercise session today. And in the exercise session today, we are going to run that more as a kind of hands-on example. And Geir, who has been working with Sean Liddick and myself on analyzing this data using machine learning algorithms, is going to show you how we actually build up the so-called design matrix, which enters the algorithms. And this, as we've been discussing back and forth, is often one of the bottlenecks when we are going to use an algorithm. How do we set up the design matrix? Now, so one of the things which many of you may not have noticed yesterday when we discussed the logistic regression and like the cancer data, one of the questions which we had in the breakout session was, how does the design matrix look like when we do logistic regression? So let's just quickly remind ourselves about that. And then, because we are going to see these things again and again. So let me use yesterday's lectures on logistic regression, because in logistic regression, what we ended up with at the end, when we set up the algorithm, was to use Newton's method, for instance, or a gradient descent method, in order to find the optimal parameters for where the derivative of the cost function was equal to 0. Now, when you look at this equation, it looks pretty innocuous. But the question is, how do we set up this design matrix? So when we did a polynomial fit, which I labeled as a kind of vanilla case, it was very easy to see how you could set up the matrix when you made a polynomial fit. And you guys been practicing in the exercise sessions, both yesterday and the 2 days before, and in setting up this design matrix. But if we think of like this Wisconsin breast cancer data, how would the design matrix look like? So let's go back to the, I think I have my, not that one, but it should be this one. Nope. Be that one. There we have. When we looked at the Jupyter notebooks for logistic regression, so one of the examples which we looked at yesterday was the so-called Wisconsin breast cancer data. And when we used scikit-learn, in a way, everything is a little bit hidden for us. So when you look at the code which we have here, we simply load the data. Now, if you want to find out what the data look like, there is a repository where you can fetch this data. So if you go to the University of California, Irvine, they have a machine learning repository. And we mentioned that yesterday and the day before. And now if you look into, if you click like on here on the breast cancer data, you will actually see how the data has been set up. You can access the data file. You see now that the number of instances, something like a 569, a number of features, attributes, or predictors. So you see there are many different names for the same thing. It's 32. And the data was donated back in 95. And it has been used, as you can see here also, there are many scientific articles which have investigated this data set. If we now go back to what scikit-learn gives us, so scikit-learn in a way loads the data and does everything behind the curtain for us. So it's sometimes it's difficult actually to see. And the design matrix here is now in this variable which is called cancer data. So if we were now to print this cancer data, so if we rerun it, what you will see then is now something like this. So every column represents one of the features. And as we did yesterday, when we looked at these features, so one of the features is like the mean radius. There's a mean texture. So you have something like 568 data entries. So along a column here, like this column, the first column which you see, you would then have the mean radius of the tumor for all the 568 cases they've been looking at. The next one is the mean texture, and these are given, I think these are given in millimeter. I think that's the features here are given as that. And the frequency is simply the number of cases which you have here. So if your design matrix in this case contains numbers of different ways of characterizing a tumor. Now, if you go to other types of data, this could be yes and no's. It could be, which are translated typically into 1 and 0. If you have other cases like numbers, which we're going to look at today, the design matrix then will consist of bit strings of the numbers. So if you have numbers from 0 to 9, you could then think of this being represented by 10 bits. So the first bit could be number 1, so you have bit 1, and all the other ones would be 0. So that's one way to encode the information about one of the variables. So I am bringing this up because I want to anticipate the kind of discussions we're going to have. So the design matrix from case to case is going to look differently. It means that you actually have to think carefully how you want to represent the data. And when you run things like scikit-learn, everything is just hidden for you. So you get an object which is called cancer, and then the object here is something which, if you look at this one, so cancer here sets up all the data for you. And then when you then do the train test split, you see now you get back a design matrix train, a test case, and then you have your data. So the data is in this cancer target. And then the way you set up your design matrix is set up in this cancer.data. And then later on, when you do logistic regression, you have your training data in here, as you see. And then, because then here you set up everything in cancer. And then you use a train test split to extract the training X matrix, the target data, and similarly for the test cases. Okay, so this was just a kind of bringing up again some of the things which we saw yesterday and which we are going to look more carefully at today during the exercise session. So as I said, the exercise session, and you all have the links to the notebooks, which was in the email. And in the exercise session, we are going to do a more hands-on and step you through the different cases. And then in the lecture tomorrow, we're actually going back to the physics of these experiments. And we will continue with this, the analysis of the data and how we set up the data matrix and so on in the exercise session on Friday. We will then go a little bit deeper next week when we go into deep learning and neural networks and convolutional neural networks. And then on Wednesday, we are going to look at something which many of you will actually are actually planning to do a project on, and these active target experiments. I know that there are at least 6 of you who have expressed a wish to do a project on active target experiments. So next week, we will actually set up all the framework for analyzing data from active target experiments. Okay, so if there are any questions about practicalities and so on, if not, we will move on to the topic of today, which is neural networks. There's a question actually whether the accuracy will always be higher for scale data. It may not happen, but normally it happens that the accuracy is there. And now it is actually, there's a question about whether it's I print the matrix before the model is assigned. What I'm setting up is this concept.data is actually what defines the design matrix, because you could see that matrix is then used in train test split to return the training design matrix and the test design matrix. Okay, so what I want to do now is to go back to the slides on neural networks, and I'm going to jump a little bit back and forth between the slides and the drawing board. So this is a very, very important field, and it's going to form the basis for the more advanced methods which we are going to look at. So what I wanted to start with is actually going back to my drawing board now, and we're going to slow down the pace a little bit, and we need to introduce many of the definitions here. So let's try to do that in a slower pace and use this lecture here to actually go through these things. Okay, so let me do that and then change. So I guess everybody can see my notebook here. And let me just do one thing in the meantime. So neural networks. And I wanted to slow down the pace a little bit so we have everybody with us, so that you can see the basic algorithm for setting up a neural network. Now, the simplest possible case is something which is called the perceptron model. And some of you may actually have heard of that one. So what's normally called a feed-forward neural network is often also called a multi-layer perceptron model. So the perceptron model is probably the simplest possible case. And the way we can think of that is as an alternative to fitting a straight line. So suppose now that we have a data set here, and which is characterized by two variables. So we could have an x1 here, and then there's an x2. Now x1 could be something like the number of hours you studied for a specific topic. And x2 could be the number of hours you slept. So what you want to find then is whether there are some correlations or whether you can make some predictions based on the number of hours you studied and the number of hours you slept, and whether you got a grade which was below or above average. So suppose the grade below average is marked by some crosses here. So as a function of x1, so these will be the data. And you have a class, and then you survey all the people which attend this course. And then you want to find out whether you can draw some line which you can use to fit. So the results above the line would be somebody who has gotten a grade which is above average. So this would be an above average. And this would be below. And then x1, as I said, is the number of hours you studied. And the x2 is the number of hours you slept. And then you want to establish whether you could set up a function here, which in this case would be a straight line, which separates the two types of results. Now, you could use linear regression here, and you could simply fit a line. So what you would do then would simply try to fit a function y, which then would be something like and now I'm going to change, instead of the beta 1s and beta 2s, I'm going to try to fit a function which has a parameter w1 times x1 times w2 times x2 plus some b. Now b plays the role of the intercept. So you could actually fit a straight line to this. The problem is that you have the possibility to find many lines which separate these two types of results which are looking after. But this is not so important now. So linear regression is something you could use now to fit this specific case. And if you think of this case, this is also a classification case. So you could alternatively have tried to use logistic regression here. Now, on the other hand, this brings us into this simple perceptron model as well. And the way you can think of this is now that you have some kind of magic box here, and then you feed in some input, and then you have an x1, which is now weighted by some w1, and then you have some x2, which is being fed in, and which is weighted by some w2 here. And then you can think of then adding this b here, which we are going to give a name, which is going to be the bias. It plays the same role as the intercept if you think of a straight line. Now then, depending on what happens inside here, then there is some function, and we're going to call this function just f. So which now takes in these input values, and then it outputs a result. So we could think of saying that this one is an outcome y, which is equal to 0. And this one would be an outcome y, which is equal to 1. So then we could have some kind of measure here that if this function here gives some kind of signal, which looks like this, suppose it looks like that, then we would say that if it's below a certain value, it just spits out 0. If it's above a certain value, it spits out 1. Now, this is the simplest possible model, which was very much inspired by neuroscience back in the 40s, in the last century. And it led to this model of a neuron. So this neuron would get some kind of input, and then depending on the type of input, it would fire a signal or it would not fire a signal. So this is called the simple perceptron model. Now, this simple perceptron model, you can show mathematically that this is something which you can use to fit a straight line. So it corresponds actually mathematically to the same thing as if we were to try to use linear regression on the data which we have here. Okay, so this is the first baby step, the simple perceptron model. And now you see that if you think this is exciting, you can now start expanding and you can make a more complicated network. So you can bring in many neurons. And this is the way we think often, for instance, our brain is set up. So you would have many neurons firing. So what we could think of then is to set up a multi-perceptron model. So that's the next step. So this normally leads to something which is called the multi-perceptron layer. So this is a MLP. You often see that name, MLP. But we are going to look at a specific neural network, which we are going to call a feed-forward neural network. So what I'm going to do now is to give you definitions of these networks. I should also say that there are many types of neural networks. We are going now to look at what's called a feed-forward. So this will be an FFN, so which stands for feed-forward. And you will understand quickly why it's called a feed-forward. And then I'm getting lazy here, so I just say neural network, NN. Now, what we are going to do then is to start with a feed-forward neural network. But what you will also see is that we have many other types of neural networks, and you're going to meet things like on Monday and next week as well. There will be CNNs, so which is a convolutional neural network. And then we have something which is called RNN, which is a recurrent neural network, which you will also meet. But then we're also going to meet other topics like autoencoders, reinforcement learning, and so forth. But the kind of basic neural networks which are widely used in deep learning are either feed-forward neural network, and then for imaging, convolutional neural networks really rule the ground. If you are analyzing things like time series, or if you want to, for instance, solve time-dependent differential equations, then recurrent neural networks have actually been used to do that. So when you do neural networks, there's also something which is called, so if you look at the simple perceptron model, you can mathematically, you can show that you can fit a straight line with that. However, there's something which is called the universal approximation theorem, which says that when you go beyond a single perceptron model, so you end up with many different layers, or at least one hidden layer, you can actually approximate functions beyond linear functions. So you can actually fit complicated nonlinear functions. So neural networks, or deep learning in general, are actually being used in a wide variety of applications. So a field which has emerged in the last 3-5 years is the solution of high-dimensional differential or partial differential equations. So for instance, if you're simulating turbulence, which is actually simulated normally by using the Navier-Stokes equations. These tend normally to be high-dimensional differential equations. And since you need to have a very, very fine integration grids, you actually end up into situations where it takes way too much time to simulate, for instance, turbulence, which is one of the top issues if you're doing meteorology, for instance, in weather forecasting. And there people have lately started to use both recurrent neural networks and standard neural networks in solving partial differential equations. So that's just one application. There are tons of applications to solving many-body problems in physics. The nuclear many-body problem is one of these, and so on and so on. And we are going to, obviously, since we have only 2 weeks, we will try to limit the number of cases we're going to look at in the lectures. So we will focus mainly on classifications, and if we get time, on some regression problems. But let's try to now look at the setup of a neural network. In principle, there's no limit to the number of layers which you can set up. But the number of layers and the number of neurons you have in a neural network, they become an additional set of parameters. So people would typically play around with different number of layers and different number of neurons. Okay, let's get a little bit started now. So let's look at the basics of a feed-forward neural network and the algorithm. So let's look at the basics. Of a feed-forward neural network. Now, what you're going to see now is that we are going to have something which we call an input layer. So these could be the function values, or as in the example which we are going to look at now, when we are going to write our own code, you will see that we are going to feed in images. And the input layer then will be the number of pixels which we feed in. So if we have a figure with the 64 pixels, that's going to define my input layer. So it means that the input layer is now we're going to just write it like this. So you're going to have a set of input nodes, down like that. So that means that we are going to have an xn, there will be an xn minus 1 up to an x1 here. So that will be the first input. So that is fed in to the network. So this is normally called the input layer. And in case of an image, we would then have the number of pixels would then define the number of input variables to the layer. So what we normally say, and this is a question which came here, so these kind of quantities, which I call nodes, you will see them in the literature, they will be called neurons. You will see them labeled as nodes. So I normally tend to use nodes, mainly because I'm not trained as a biologist. Some people will also call them units, and maybe there are other names. So I will oscillate between neurons and nodes, and sometimes I may even say units. So when I say neurons, it's the same as nodes. So we would have the input layers. So that defines what we're feeding in. And the thing you should keep in mind now is that when we do supervised learning, so if you were to do unsupervised learning, like using things called Boltzmann machines, then these are called generative models because you regenerate the input variables. So input is not changed. So that's fixed. And as I said, these could also represent the x values of a function which you want to fit by a neural network. Then we obviously have the hidden layers, and we can have many. So in the hidden layers, we will have, so we can have a given quantity, so that's a variable. You see the input layer is fixed by your physics applications. Now, the hidden layers, the number of hidden layers becomes a variable. So in each hidden layer, you can then define, and this becomes a variable. So this is a variable again. Define the number of neurons or nodes. And that doesn't need to match what you have in the input layer. So when we go up again here, we could now think of having an input layer, a hidden layer, so the first hidden layer, like this one. So this is the first hidden. And then we have a given set of nodes or neurons in here. So then each of these neurons receives a signal which comes in from every node in the input layer. So X1 feeds into the first hidden layer. So there will be a hidden 1, there's a hidden 2, there's a hidden 3, and then we're going to put a label 1 on top here to indicate that this is the first hidden layer. And these numbers don't need to be the same, so we end up with an M here of the first hidden layer. And everyone here feeds into these nodes in one way or the other one, like that. And then I'm just drawing dotted lines here to indicate that all the other input nodes, they send a signal to the first hidden layer. Now, this is a feed-forward neural network. And the reason why we call it feed-forward is that there is no backfeeding from the hidden layer back to the input layer. You can make more complicated layers. So like a Boltzmann machine is actually a machine where you can have crosstalks between the nodes in a given layer. You see also there's no crosstalk between the nodes or neurons in a given layer. So it's just a plain feed forward. So more complicated neural networks like a Boltzmann machine, they could have a backfeeding. So you could have a signal which is being sent back. You could also have a crosstalk between the nodes in a given layer. Now, the thing is that when you do now, when you have such crosstalks, what happens then is that the training of the network becomes much more complicated. So these are linked now with what we call weights. So let's bring up a new color here. So we would have a weight here, W11, which now feeds into this. So there would be a weight W12, which goes to the second one, W13, which goes to the third one, and so on. And the weights, so we have now parameters here. So we have the number of hidden layers, that's one parameter. We have the number of nodes, which is a parameter. And then we have the weights. This is a new parameter, new set of parameters. Then every single layer here has now a set of so-called biases. And that plays the same role if we now go up a little bit. When you look at this quantity which we had here, which for a single line could be thought of as the intercept of the line, this is normally called a bias. And the reason why we need this bias is that sometimes the weights which feed in to a given layer, they could by accident be equal to 0. And then if that happens, then nothing propagates out from that layer. So then the training just stops. So in order to hinder that, what we have then is something which we call a bias. So I'm just going to write it like this. So it's going to be a B. So this bias could be the same for every node in the layer, or it could have a specific value which now refers to every single node here. So we could have a B of I here. So that means that every single node here has a different bias. So often what you will see in many codes is that you set this bias to be the same for all the nodes in a given layer. But this is something which you can change when you set up the code. So the matrix for every hidden layer then, as there's a question here, for every hidden layer, there will be a matrix, a weight matrix of size n times n. So the relation between these n's and m's, obviously when you have the input layer, that's something which constrains you. So the input layer is fixed. That is your physics case or the type of case you want to train, which determines how many input variables you need. So as I said, if you have a picture which is 8 times 8 pixels, that means that you have 64 pixels, then you need 64 input nodes. And you need to specify that when you set up the network. So later we will see how we can use Keras to actually define a network pretty easily. So there is no kind of magic number of hidden nodes. So this is something you can actually play around with. It becomes what we normally call a hyperparameter. So if you felt there were many parameters yesterday in logistic regression, now we're getting even more parameters we can play around with. Now the next thing, so we have defined the weights. So this is actually something which becomes a matrix. So we can set up a matrix. And that depends on the number of, obviously, nodes which we have in the hidden layers. So this kind of, the nodes which you have here, they would now fire a signal to the next hidden layer. So we would have a hidden layer with a H1, 2. So we would have a new one here. And that could also have a different number of nodes. So we could have an N of L here of 2 to indicate that this is the layer, hidden layer number 2. And then this would continue. So you would send in signals in here to all these. And then you would have a new matrix. So this would then represent, this will give you an M times L matrix. In the previous case, you had an N times M matrix for the weights. There will also be a new set of biases. So we need to put this one of 1 here. And then there will be a new bias, a B of I of 2 here. And then we continue like that till we reach the output layer. Now you clearly see here that my drawing skills are not very great, but I hope you understand what it's supposed to mean. So you see what kind of topics in elementary school I never did very well in, but I hope you understand the basics here. Now the hidden layers is, the number of hidden layers is something you have to play around with. And the way you would typically do that is to think of the number of hidden layers as a parameter. And then you would look at the, let's say if you're doing classification, you could look at the accuracy, or you could look at the confusion matrix and so on. And then simply treat the number of hidden layers as a parameter. So there is no kind of magic setup unless you know that your function is a straight line, because then you can just get away with a simple perceptron model. Or rather, if it's a straight line, I would never care to do a neural network. I would simply use linear regression, period. Now, the bias, so we are going now to set up the mathematics here. So let's just set up the definitions, and I see there are many questions coming up. So after we've done the definitions, we're going to see how we can set up the mathematics of a given layer, and because we need to define some more quantities. So we have the bias. So this is a new set of parameters. We can decide to have a bias which is given to be different for every single node in a layer. or we can have it to be the same. So in principle, this is a vector of unknowns. So we would normally set everything using some kind of random number generator, and we would just initialize the weights and the biases. So they have to be initialized in one way or the other one. So we normally call these hidden layers, because what we would have in between, so at the end here, there's going to be an output layer. So that would be the final one. And that has also a given number of nodes, but that is fixed by your output. So if I want to use my neural network to classify the 10 handwritten numbers from 0 to 9, the 10 numbers, then I can have 10 outputs. If I'm just looking at the yes and no case, there's going to be one single output, like this case where I got a grade which was below or above average. So that would be a typical 1-0 or binary case. Then I would just have one single output. So depending on what you want to do, you can actually have one or many types of outputs. So if we now want to redraw the network, so what we would have then, if we now use different colors here, so we would have the input layer like this. So we would have an input, and this is fed into the network. And then at the end, we have the output layer. So it means that suppose now that we have only one type of output. So this could be a yes and no case. So it means that what we have now is just one. If I'm thinking of the different numbers from 0 to 9, I can have 10 outputs. But let's now suppose we have one output. So this is my output of the network. And this is my last layer. And in between here, what we have then is just a set of hidden layers. So we can have many such hidden layers. And then we have another ones. And then finally, we have the last layer. So I'm going to put labels here. So this would obviously be the first layer. This is the second one. And then there's a layer L here. And then the final layer is a layer which I'm going to note with L, uppercase L. And then I have an L -1 here. And clearly this layer feeds also into this one. So they all feed forward like that. So this feeds in here. I'm not going to put up all the arrows here. This feeds in, and so on. So we call these hidden layers because, I mean, these are the layers between the input and the output. The output and the input are specified by your physics case, or the case, the example, or the case you want to apply the method to. Then what happens here is that at the end here, this output is then compared with our target. So these are our target values. In the case of a binary case, the target values are just ones and zeros, or -1 and 1, yes and no, depending on what you define. No, I mean, you can actually decide. I mean, people will play around with the number. There's a question whether the number of input nodes have to be more than equal to the number of nodes in hidden layers. I mean, that is not necessary. But sometimes you put them to be equal, and sometimes you do not. Sometimes you have more hidden nodes, and so on. So these become parameters which you have to play around with. So when you start looking at things now, what you have the bias as a parameter. You have the weights. So this is what we are going to train. So the training, so in our training, these guys here are the ones which we are going to use to define the final model. Then we have the number of hidden layers, which becomes a parameter. And in the hidden layers, we have the number of nodes. So that's another parameter. And then we can add these hyperparameters, which we discussed in connection with logistic regression and linear regression. So that brings in additional parameters. Now, there is another set of functions which we need to think of. So when you send in a signal here, so suppose this is a given node here, let's call this node I. So this node receives input from all the nodes in the previous layer. So this variable here is a variable which I'm going to call now what is being fed in here. So if we magnify it, so we now have a specific node, and that receives inputs from all the previous nodes, and then it sends out a signal. Now what's being fed in here is something which I'm going to label as a ZJ, and then since I am in layer L, I call this ZJL. Sorry, this let's just call this J. So this is node J of layer L. Then this quantity here is something which I now can define as a sum over I equal to 1 up to m, which could now be the number of nodes which we have. And then there's going to be a wij, and then for L, the layer L. And this is now multiplied with the output A of I of L minus 1. So what is this A of I of L minus 1? So this quantity here is actually the output from a node I in here, in the layer L minus 1. So that one is an output from that specific node. That output comes into this node as J in layer L, and it's weighted by these weights, which are unknown quantities. And then finally, there is a bias, Bj of L, which is an unknown parameters. So the parameters of the theory, which we need to fit now. So we need to fit that one, and we need to fit that one. So these are the parameters which we need to fit. Now, this quantity A here is now given by the output of a given node in the previous layer. So this set J, this feeds in and produces an output. So this output here is something we would call AJL, and that's given by a function of set J and L. And now comes a new parameter in the theory. So we would have a new parameter. So this is a new parameter. So it's actually a function. So in a sense, it's not a parameter, but I'm just going to loosely call it a parameter. So that's a function. And one of the standard functions which we have, like the one we met yesterday, so a typical example, f could be the sigmoid function. And as we will see later today, the type of function here is something which brings in another complexity to the neural network. And you will see then that when we run a neural network, we can actually play around with different activation functions. So this function which you see here, this one, this is called an activation function. And that is it gives you another parameter. So I guess now you're getting pretty confused. I actually, and many people actually get disappointed because, well, they say, hey, we're just playing around with tons of parameters here. But that gives you a lot of flexibility, and also the kind of functions which you use, you would like them to have some mathematical properties which perhaps could reflect the physics you're looking at, but mostly you would like them to produce analytical derivatives and continuous functions. So the parameters we have now, the parameter space, so we have an activation function, it could be a sigmoid, it could be a tan H or any other type of function which one would think appropriate for a neural network simulation. So that's another parameter. So we have that one. We have the weights and the biases. So the weights and the biases are going to be the output of the training. Then we have the output, which is defined by the physics of the problem or the specific case. We have the bias parameter, weights parameter, number of nodes becomes a parameter, number of hidden layers becomes a parameter. The number of input nodes is fixed by your data set doc. So now the question is, and I see that there's a question in the chat box here, how do we define, so how do we calculate? Do we compute the weights, Wij, and the bias? So the recipe here is the backpropagation algorithm. Which is just a repeated application of the chain rule. Plus gradient descent. Now, when you construct more complicated neural networks, what you will see is that when you construct more complicated ones, at the bottom, at the heart of the network, there's going to be a backpropagation algorithm. Okay, so let's try to repeat now. So the input to a node, and now we're going to set up the backpropagation algorithm. So the input to a given node, to node J, in layer L. That specific node, this input is defined as set J, L, which now contains a sum over I, 1 up to the number of nodes which we have. There are the weights which connect the previous layer with a new one. So we put that L, indicate that this are the weights with respect to that specific layer. And then we have the output from the previous one, which is L minus 1. So if this is the input node, which feeds into the first hidden layer, then the A's would simply be your input values. And then we have the biases of BJL. So the number of nodes which you have here is obviously a variable. And then we define the output from node J, the same node, in layer L. So that output is something, so these are variables which we're going to define now. So that's going to be AJL of an F of ZJ of L. And that could be the sigmoid function. So if it's a sigmoid, this would be just be E ZJ of L divided 1 plus E of ZJ of L. So that would be the plain sigmoid. Now what we are going to do now is to apply the chain rule. So chain rule applications. We need a backpropagation algorithm. And what we need to do now, so what we're going to do now is to look at L. So let L be the output layer. And the output layer is what we called L. So what we need is to define, so we're going to do a, here we're going to do a regression case, regression. And what we have then is a cost function, which now will depend on the weights. So I'm skipping the subscripts. It will depend on the weights in the final layer, and it will depend on the biases in the final layer, B of L. And if we are doing a regression problem, what this is going to look like, and now I'm going to skip the 1 over n. I'm just going to take the 1 over 2 here to get rid of that one when I take derivatives. So that's going to be given by a sum of I equal to 1. And these are the outputs, n. It doesn't need to be the same as the inputs. Remember that. Then I have my final output. So there's going to be an AI of L. So that's the output from node I in the last layer. And this is now going to be compared with the target values. So the target is what I want to produce. So I'm not going to call that for I, but I'm going to call that for T of I. And this is squared. So we're going, so this is just nothing but the mean squared error. So that could be an example of my cost function. So what I want now is to calculate. So I need, because I want to minimize this function with respect to the weights and the biases. So what I'm looking after now is a derivative of D of C of WL and B of L with respect to, so I'm writing this more now in terms of matrices and vectors, and D of C of WL of B of L of D of B of L. So these are the quantities which I need to calculate now. And that's where a repeated application of the chain rule comes into play. So what I'm going to do now, just to show you how we can do this and how we end up with a final algorithm for setting up a neural network. So let's go through this. Any questions, by the way? Before we just set up some of the aiding quantities. We need some quantities here which we need in order to set up the final back propagation. So T of I here.
Can I ask a question?
Yeah, go ahead, please.
Yeah. Actually, maybe I didn't get exactly the difference between this Zj of L and the activation function A.
Yeah.
Why again be a function of Z?
So Z, if I understood correctly, so let me just find the one thing. So C is actually the input to a given layer, and A is the output. So you could now think then when you look at the given node, so you have a specific node in a given layer here, and that receives a total input value, set J. So you could think of this as a voltage. And then you feed that voltage into a function. And that function tells you that, okay, if the voltage, it could be a step function, which you feed this voltage into. So you could think of a neuron, which receives signals from many other neurons, nearby neurons. And the neuron then accumulates all these inputs. And then based on, if these are voltages, based on the total voltage which comes in, it decides that, okay, if it's below 0.5, just as an example, it doesn't fire a signal. If it's above, it fires a signal. So this A, which you have here, you could think of that as given. So I'm going to mute you guys because there was some background noise here. Now, T, on the other hand, is the result you want to reproduce. And normally that's called the target. So that's why I label this as a T here in the function here. So this is the target. value you want to reproduce. We've also used a y of I before. That's what we used before. So if we were fitting a function, this y of I is normally the way we labeled it. But in this case, we're going to just label it as a t for the target. This is the target value we want to reproduce. So the network spits out a value, and then we need to compare that value. So every time we feed a signal forward, we end up with a final output, and that final output is then compared to the target. So the target is the value we want to reproduce. So what this function here now measures is how well our network is in predicting the value t of I. So if there's a large discrepancy, clearly we are doing badly. So what we need then, since this now gives us a kind of gauge, a handle on how well we are doing, what we need now is actually to train the weights and the biases. So what we are going to do now is actually to step back all the way to the first hidden layer. And in the backstepping here, we are going to compute the derivatives of this cost function at every layer. Then we reach the first layer, and then we have updated the values of the biases and the weights. Then we feed the signal forward again. And then with this new feed forward, we produce a new output A, and this is again compared with the final target. Now we have tests then, which tell us whether we are happy or not with the final result. If not, we would continue this training. We would propagate backwards. So this is the back propagation algorithm. We would propagate backwards, and then till we reach the first hidden layer, and then we move forward again and produce a new output, which is compared with the target value we want to reproduce. So it goes back and forth like this, and the back propagation algorithm is the one which now is going to update the weights and the biases so that this quantity here is as close to zero as possible. This is the ideal which we want to have. So this is the way a neural network is trained. So there's a back propagation phase where we train the weights, and then there's a forward propagation where we produce an output which is compared with the final target value. So this feed-forward network contains the back propagation. So feed-forward neural network means that the signal is sent forward. There is no link with previous layers. So a new layer send the signals only forward. Then when you reach the final output, you compare your output, which has been produced by the parameters of the network, with the target value. You compute the derivative of this function here. And then clearly, if this derivative now is below a certain value, you would stop. If not, you propagate back. You get new weights and biases, and then you have a feed forward again. And then you go back and forth like this till this cost function here reaches its ideal, which ideally should be equal to 0. So there's a question here with the whole neuron. So we're going to take a small break now so we can take questions. So what I wanted to do here is actually to go through an exercise in the chain rule. And this may not be the most exciting thing we are going to do, but actually the back propagation algorithm is just a plain exercise in the chain rule. So what we need now is to calculate these quantities here. And clearly for the final layer, since we're going to compare that with the targets, we want to, what we want to is to minimize this mean square error and have it as small as possible. Okay, so let's do the mathematics. It's not very exciting, I promise you. It's pretty boring actually. And if you peep into the slides, you will see the same things. But I just wanted to step you through the basics here. So we need some intermediate steps in order to do this. and I'm just going to set them up. So what we need is to, when we are computing the derivatives of the cost function, so we would need the derivative of set j, and now we can put that one for any layer. So it's not only the final layer. So we're going to need that one for a wijl. So if you look back at the equations which we have, so this is a helping quantity, a help quantity. You see now I have d set j. That's going to enter the definition of my derivatives of the cost function. And you see now that if I take the derivative with respect to wij, what I'm going to get is this quantity here. So that's pretty easy to see. So that gives me a of I of L minus 1. Then I need a derivative with, so this is another quantity, an intermediate quantity, which I need when I'm going to derive the equations. d of I of L minus 1. And that ends up being just the weight. Like that. So that's one quantity I need. Then when I take the derivative, another quantity which I'm going to need is the derivative of the output from a given node in a given layer. And I want that as a function of this set j of L. And if I use the sigmoid function, this is going to be equal to a of j of L of 1 minus a j of L. So with the sigmoid, this is actually f set of j. That's nice, but it can actually be a general one. Doesn't need to be the sigmoid function. So the thing I would need to change if I change another, so this is from a computational aspect. So when I change my activation function, I have to be a little bit careful in order to see what the derivatives look like. So the things I would need then would be to find the derivative of the specific activation function. So if we now go back and let L be equal to L, so that's my last layer, then my C of W of L and the bias of L is something which is equal to 1 over, and then I just write I here. I'm getting lazy, too many indices. Minus the target, T of I. And then if I take the derivative of that one, of dC, of D, of Wj, of K of L, this is simply going to be A of J of L minus Tj. So that's my target. And then this is multiplied with D of Aj of L, of D of Wj of K of L. And now you see I'm going to need one of these quantities which you see up here. So this kind of intermediate quantities which you saw here are quantities which I'm going to use now. So you can, this quantity here is now going to be given by D of Aj of L and I have the expressions for these, dj of L, of D, I'm just using the chain rule again. So I promised you guys, this is an exciting exercise in the usage of the chain rule. So it's going to bring you all back to what you saw in kindergarten, when you were stumbling around in kindergarten with your napkins and so on. And then you're one of the first things you saw and you heard about in kindergarten was actually the chain rule. I guess you all did that, didn't you? Right? Okay, then the you see, you guys are being exposed to all my lame jokes, eh? Don't take me too seriously. Okay, so we can rewrite this one in terms of Aj of L, and then I would have minus 1 Aj of L, and then I would have the value in the previous layer, L minus 1, the layer before the output layer. So what I did was simply to put in the expressions for these two guys, these kind of intermediate quantities which I mentioned up here. So I have this quantity which I'm being using, and then I use this quantity which you have here, this quantity. And when I bring everything together, then I have a derivative now for the cost function in the final layer, WL. I'm skipping the B value, and that's given by a WJK of L, and that's going to be an A of J of L minus T of J, and then it's an AJ of L minus 1 of AJ of L, and multiplied with an AK L minus 1. And it's common here to actually denote this one, denote a quantity. So this quantity J of L, and you will see that in the slides as well, now is a quantity which absorbs some of these quantities, AJ of L, multiplied with AJ of L minus T of J. And that's going to be equal to F of set J of L. So it's a derivative of the cost of the activation function. So if you have a new activation function, the thing you need to have in your code is an expression for the, is a code for the derivative of the specific activation function you're using, like that. So that means that my derivative of C of W of L, the output layer, of D of WJK of L, is actually given by this quantity J of L of an AK of L minus 1. Then what you can also show, and I'm just going to put it up here, is that this quantity here, this delta J of L, and you can see the derivation in the slides, is actually not so difficult to show that. Then this one can be actually be given by DC of D of this bias of J of L, the specific layer. So what we have now is the derivative at the last layer of the cost function with respect to the biases and with respect to the weights. And we have analytical expressions. And the having the expression for the activation functions, which give you analytical derivatives, is very, very important. Okay, somebody asked me what kind of kindergarten I went to. I didn't go to a kindergarten, guys. I was a lost case. They didn't even accept me in kindergarten. Sorry for that. Okay. Okay. I'm trying to get some serious again. Exactly, that explains a lot. Guys, I didn't tell you. I come from a part of Norway, or rather my mom comes from a part of Norway, where they actually claim there are more sheep than humans, and we speak accordingly. So last year, that county lost the record, and people were pretty depressed that they were only the second-ranked county when it came to the number of sheep related to the number of humans. Fortunately, I have relatives from Shetland, and there they really are, the Shetland Islands, there really are more sheep than humans, and we do speak accordingly. Okay, guys, that's I'm not gonna continue along these lines here. Okay. Anyway, so the thing which we need now is actually to find out how this delta J, what we need now is actually delta J as a function of L. We have fixed it for the output layer, and we would like to, what we're going to need now is to use the chain rule. So we can actually show that this quantity here is going to be given by DC, and then with respect to the derivative of the input to the specific node. So what we're going to use now is just to perform a repeated use of the chain rule. So that's going to be given as a sum over k. And now what we want to is to have something which feeds back to the previous layer. So we would have a set k. So this is just a repeated usage of the chain rule. So layer L plus 1. So we fixed everything for the final layer. And then we need, using the chain rule, we're going to have this quantity here. And then we need this one as a function of set j of L. Now, this quantity which we have defined here is the same as this. So k of delta k of L plus 1, which we have. So suppose L plus 1 is the final output layer. This is fixed. And then the quantity which we need next is this d set k of L plus 1 with respect to set j of L. And we know that this set, if we just write it like this, so L plus 1, that is given by the previous value. There's a sum of I, the number of nodes, the number of nodes in the layer L. And then I would have an ij of an L plus 1 of A of I of L plus this bias of j of L plus 1. And you see now that if I take the derivative of this quantity here, the way it's put up here, then this function here is actually an f set j of L. And that means that what I end up with is that this j of L is now given as a sum over k, and then I have the derivatives from the previous layer of L plus 1, and then I'm going to have the weight of kj of L plus 1, and then multiplied with the derivative of the activation function. So that was the final equation which we need. And what I wanted to do now is actually to bring everything back to slides so that we can summarize things and look at the algorithm. So let's try to do that now. So let me go back to the slides. So you should see them now. So let's go up a little bit and try to summarize what we've been doing. And then we're going to look at how to write our first code based on this. So let's go up a little bit. So what we have done till now is to so when we set up the backpropagation algorithm, we are going to end up with a given set of equations. So this is the final equation which we need. So when you're setting up the backpropagation algorithm, we need then to first set up the input data and the activation function set1 of the input layer, which then feeds into the first hidden layer. We need to perform a feed forward, which will reach the output layer. And then we compute all these inputs to the different activation functions for all the layers, 2, 3, up to the final layer. Then we compute the output error for the final layer, so which then is proportional to the cost function, as you see here. Then what we do next is that we backpropagate everything by using this quantity here till we reach the first hidden layer, which is indicated by 2 here. So the first layer is now my input layer. That is unchanged. So what we need then is every time we move back is that we update the weights. So we would have the weight here, and this is where this eta here is now the learning rate when we are computing the gradients. We have the derivatives of the weights, as we found a little bit higher up. If we go up here a little bit, we found that the derivative of the cost function with respect to the weights is given by this quantity here. So that means that we need to code this function, include that one. We are using a gradient descent, and that means that there's a learning rate. So this eta, which you see here, is a parameter. And then we have a similar updating rule for the biases. So we have an initial guess, and then we have the derivatives. And these quantities, which you see here, delta J of L, is the quantity which is computed here. And that depends on the results from the previous layer, or the layer ahead of it. So if L plus 1 is the output layer, then these are the weights in the output layers. And this will be then the updated derivatives in the layer before the output layer. And then you proceed like this to the final, which is actually the first input layer. By this algorithm, which you see here, then what you have is a update of the weights. When you have reached the first hidden layer, then you start again. And then you do a feed forward with the new values for the weights and the biases. And then you continue back and forth like this till your cost function, or which is our case in the mean squared error, is as small as possible. And then we would stop the training. Okay, so if we now want to set up an algorithm, so let's try to do that. And let's use the rest of the time to see how we can actually set up an algorithm for doing this. And now I want to switch, I'm going to switch to the Jupyter Notebook. So if you look at the slides here, what I'm doing now on this list of slides, I'm just jumping into this Jupyter Notebook, which we have here for day 4. And we are going down a little bit till we reach the setup of the code, so you can go through the basic steps. So let's do that. You will see these equations again. So when we're going to set up a multi-layer perceptron model or a feed-forward neural networks, what I'm going to switch now is the classification problem. So the case we looked at now is for a regression case, but now we also want to do classification. So if we bring back the sigmoid function, which we had when we looked at the binary problem, this would be the probability. And then we would define the cost function as we did yesterday in terms of the cross entropy. So we would take the log of the product of probabilities, and then we end up with a cost function, which is something which we can deal with in the actual calculations. Now, in a multi-class calculation, what we need then is something which is called a softmax function. So what we would typically encode the data as, so a number like 5. So we're going to look at the MNIST database, so which is a set of handwritten numbers from 0 to 9. So we would have 10 numbers, and we're going to encode them in terms of a bit string. So a number like 5, you would now see would be encoded like this. And a number like 1, so this would be 0, 1, and the rest would be zeros. So we would have a binary bit string of length C, where C is equal to 10 is the number of classes in the MNIST data set. So these are numbers from 0 to 9. So as I said, the reason why we bring up these different ways of doing things is that every case you're going to look at will have different ways of setting up your input data. And as we said in the beginning, difficulty often is to be able to set up the input data properly. So the logistic function, which the modified logistic function, this softmax function reduces to the standard logistic function for the binary case. Now I'm going to scroll down a little bit now because I'm not going to go through some of these details I actually have set up. So the softmax function gives also a derivative which is pretty similar to the the one from the sigmoid function, except that in the sigmoid function we had 1 here instead of this delta ij. Now let's look at how we develop the code. So when you want to develop a code, these are the things you need to think of. And you will see that in this afternoon also when we go through the specific example which is related to the beta decay data. So you need to collect and pre-process the data. That's define model and architecture. You have to pick the cost function and the optimizer. So what kind of method you want to optimize. We use the optimization. We want to do a stochastic gradient descent. You want to use a momentum-based stochastic gradient descent and so on. And then you also need to later to train the model. You need to evaluate the model performance and test data. And then we have hyperparameters, like this regularization parameter. Now, what we are going to use now is the MNIST dataset. So that's already available through scikit-learn in the package there. And there are tons of examples. So this is not something which I've cooked up myself. Actually, I've done it together with many other people. But the data contains 70,000 images and they're 28 times 28 pixels. If I'm going to run this in due time, I have to reduce the data set because the matrices would be too large. It would just be running for an eternity. So I would need to reduce the data sets, and the data set which is in scikit-learn contains roughly 1,800 images, and the images have been reduced to 8 times 8. So when you're setting up the data now, the thing now is that you need to set up a design matrix which contains the inputs and the features, right? As we have discussed before. So each row represents an input, in this case, a handwritten digit, and each column represents a feature, which is a pixel. So this is the way we are going to set up the data. And you will find this useful when we move later this afternoon to the beta decay data, because these are actually given by pixels from a detector. So these are images. So what we have then would be inputs times features. So a simple example is if you look at the body mass index. So you would have the height and the weight of people. So this would be your matrix. So you have one feature, which is your height in meters, and then you have the weight in kilograms. And then your output or the target would simply be the body mass index, which is calculated based on the weight and the height of people here. So in our case, each input image is a 2D matrix. What we normally do is to flatten the matrix into a one-dimensional array to turn the data into a design feature matrix. So we lose some spatial information in this specific case. So when we come to more complicated architectures like convolutional neural networks, they can actually take advantage of such information. So what I'm going to present to you now is not the best possible way of dealing with images. So what I'm doing now is to simply load the data set. So the data set is now the load digits. And I'm setting up the inputs, and I'm going to have the labels, which are my targets. So if I run that one, and then I make a small plot, you can now see that my inputs, I have roughly 1,800 images, as 8 times 8. And then you see now that the inputs, the design matrix contains the inputs, the images, and the number of features, which will be the pixels. So these are now reduced images, and it's not easy to see here and what is what. And for somebody like me who always struggles with colors, so when I venture beyond black and white, then everything is just a soup. So, but I think I can see a number 8, 7, and 3. So the next thing we do now is to train, test, and to split things in train and test data. So I say the train size is equal to 0.8. And then we set up everything in according to that. And the thing which we do next is to set up the training data and just spit out the amount of data which we have. And you see now that the number of training images is the 80%. The next thing we need to do now is to define the model. And in our case, we need to define what kind of activation function. So in this case, I didn't normalize the data. This is something you would plug in a little bit later. But in this example here, I did not normalize my data. But normally you would actually do that. So that's an important point, which I didn't put into this code here. So I need to define the architecture. I need to define how many layers I want to have. I need to define what kind of activation function I want to have. When I define the layers, I need to define my input layer. So each input image has 64 pixels. So that means that we have an input layer of 64 neurons. I have my hidden layer, and that will contain now 50 neurons. I'm going to only have one. So this is the architecture, right, which I'm setting up. So my hidden layer has now 50 neurons. I have 64 inputs. So that means that the weights which I need to fix are 64 times 50, so 3,200. That's the amount of hidden of weights. And then I have my output layer. So in our case, we have 10 outputs. So it means that my output layer needs now to have 10 nodes of neurons in the output layer. So that means that what I have then is, since I have 10 neurons or 10 nodes, and I have 50 nodes in the hidden layer, it means I have 500 additional weights which feed into the output layer. So at the end then, when I'm setting up my network, I have fixed the number of biases and weights. I need to set up the biases. And in this case, I'm doing this in a poor way. So this is more, I'm just fixing it to 0.01. But normally I would typically use a random number generator, which would fix the weights. And right now, I'm just putting the weights to be the same for all the nodes in a given layer. So you see now I'm setting up my variables, number of inputs, number of features by this X-train shape, number of hidden neurons, 50, number of categories, 10. Then I'm setting up my hidden weights, and I'm just giving them a random value using a normal distribution. And you have the number of features and the number of hidden neurons. So that's the dimensionality of the weight matrix. And then I'm setting up my bias. And I do the same thing for the output weights and the output bias. And now I've set up my network. I define the parameters of my network here. And with that, we are now ready to start building the code. So we need to perform a feed-forward pass. So we would have the inputs to the given hidden nodes. And then we produce an output. And we have a similar one for the for the output layer. So this is the input to the output layer. We have 10 nodes for the output layer. And then we have the output from this input to a given node in the hidden layer. And essentially what we end up doing now is to perform a set of matrix multiplications and matrix vector multiplications. So to have efficient codes for doing that is very important. So I'm going to go a little bit fast through many of these things here. So you see now the way I'm setting up the code. So I'm running through here. I'm setting up my activation function, which is the sigmoid. This is my feed forward pass. I'm setting up my input to the hidden nodes. So the H is the hidden nodes. I get the output from the hidden nodes. And you see now this one, this H is now fed into the output nodes. And then finally, my final output is given by the softmax function, which is now given by these probabilities, which has this exponential term, and then the sum of the different exponential terms. And that's the one which now is the feed-forward part. And that produces my final prediction for the feed-forward network. And that's being compared to the final output. Then when we choose cost function, so I'm going to skip through some of these things. I want to, I just need to run the codes, by the way. So the last one I run was this one. And then, so let's do that. And then we continue like this. And we are setting up now the, doing the first performance of the model. So what I have is my feed forward part, which is in here. And then I have my back propagation part, which is now set up here. So I have my, produce my different derivatives. And then I move on. I set up my variables. So I would now have a, in the back propagation, I'm setting up my learning rate in here. And I also have a hyperparameter lambda, which I put to 0.01. So if I look at my first case here, when I made my feed forward pass, this is what I got. And then I did my first training with those types of hyperparameters, and that doesn't look very impressive. So I want to have an accuracy which is equal to 1, and I have 0.09. So the next thing I would do now, since I put a learning rate equal to 0.01, and I had this hyperparameter equals 0.01, it may not give me the best set of hyperparameters. So what I'm going to do now is actually to train my network with a series of different regularization parameters and a series of different learning rates. So I have a slightly better code here. When you move down, you can look at this in more detail later. But the thing which I wanted to mention is actually this accuracy score, which I'm looking at now, simply counts the number of correctly classified events. So ideally, it should be equal to 1. And you saw in my previous case here, that was not very impressive. I had chosen a set of hyperparameters, which were probably not optimal. And the new accuracy in the training data was not, it's not something you would bring forth to people here. So what I'm going to do now is to make a run where I now introduce my neural network code, where I also use a stochastic gradient descent. I have my accuracy score in here. So I've actually been training this model with a program which we've been writing ourselves. And in this case now, when I do the stochastic gradient descent, everything looks a little bit better. I train now with the learning rates, which go from 10 to the minus 5 to 10, and the same with the hyperparameter lambda. And then I rerun things. And you will see now that you will get different learning rates as you move on. And you will get different accuracy scores. Ideally, you should be equal to 1. This is not the best way of visualizing the results by just going through them. So a better way is actually to use Seaborn, the Seaborn package, and run through that one. But you see now for certain learning rates and some hyperparameters lambdas, you're getting slightly better results. So if you use Seaborn, on the other hand, it's a little bit easier to visualize the results. So it's just rerunning things here. And now you see on the training accuracy, you will see now that for a parameter eta, so this is the learning rate, which is 10 to the minus 3. we get a training accuracy, which is pretty good. It's actually 1. And then on the test accuracy, this will be the test data, still with a hyperparameter or learning rate 10 to the minus 3, and a lambda parameter, which goes from 10 to 10 to 10 to the minus 1, 10 to the minus 2, 10 to the minus 3. We are getting results which are pretty good on the test data. So this is actually not so bad on this specific case. Then scikit-learn has its own MLP regressor. So lambda is actually the hyperparameter, which is the same as we used in linear regression when we looked at ridge regression. So you can add regularization terms on your parameters. You would typically do this on the weights. And in this case, what I did was to implement a norm2 hyper regularization parameter. So this would be like if you were doing ridge regression, but instead of having the standard ridge regression or the standard linear regression case, you would now have a neural network. So the lambda is actually a regularization parameter. And eta is my learning rate. So as you see now, you're getting pretty many parameters. If you go back to my neural network, what we have is a space of, so we are doing a grid search here for parameters. We are performing a stochastic gradient descent with a given batch size and a given number of epochs, so that becomes also a parameter. So you will see here the parameters which feed into my own code: learning rate, we have the regularization parameters, the epochs, the batch sizes, the number of hidden neurons, and the number of categories, which is fixed by the data. I have only one hidden layer, so that would be an additional parameter. And furthermore, if you look at my model here, what I have is a, if you go up a little bit, you will see that my activation function is a sigmoid function. So that's already baked into the model. And that would be another parameter. So if we can repeat, so this is my own code. And then you could run everything using scikit-learn. And in scikit-learn, what you need to specify then is obviously, again, the number of these parameters. So you would have the number of regularization parameters, the learning rates. You need to specify the activation function. And by default, it takes a stochastic gradient descent. So that's the default method. And then you can run the network with scikit-learn. But scikit-learn is actually limited because it has only a feed-forward neural network. So if you want to use the more advanced methods, that's where we actually need to use TensorFlow or PyTorch or similar methods. If you want to visualize again, you can use then Seaborn, and you will get the same kind of visualization of the results which we had with the code which I have written. But now you see that scikit-learn is actually doing a better job. And you see in this case, if you go back to my own code, you see now that in my case, when the learning rate was 10 to the minus 2, I got a training accuracy which was less than 1. Whereas scikit-learn has it contains a stochastic gradient descent, but also with an optimization of the learning rate. So it takes the learning rate as an input, and then it tries to optimize the best possible value. And you see in this case, we have a much larger window for the learning rate and the accuracy score. And then if you look at the test accuracy, you see also that the test accuracy is much better than the one which I had in my code. You're actually getting pretty close to 1. So my code serves only as an illustration for how you can implement a neural network. But clearly, if you want to do neural networks, I obviously recommend using more professionally written code. Now, the standard, and this is what we are going to use now for the rest of the time, is TensorFlow, and then there's a wrapper set, which is called Keras. And Keras is a very nice interface, which makes life a little bit easier. And then yeah, that's a good point from on the chat here. When we use the regularization parameters, if you remember when we did ridge regression, you could actually show that you can get a smaller mean squared error when you tune the regularization parameter. So it's a way for you to reduce the mean squared error if you're doing regression, or to get a better accuracy. You're actually reducing the variance of the problem. So TensorFlow was released by Google back in 2015. Now there's also another very popular library, which is called PyTorch, which was developed by Facebook. Now TensorFlow seemingly has a little bit more functionality. So if you're solving differential equations, it has more optionality when it comes to finding gradients of functions than PyTorch has. But there's some kind of competition between TensorFlow and PyTorch, and people, we are not going to pass a judgment on whether you should use TensorFlow or PyTorch. But PyTorch has really, how to say, it's been very powerful when it comes to flexibility with respect to different methods like convolutional neural networks, recurrent neural networks, and so on. So you would need, if you're using Conda, and probably many of you have already installed TensorFlow, and then if you're doing that on your own system, you just do pip install TensorFlow. Or if you're using Conda, Anaconda, just Conda install TensorFlow, and that should give you TensorFlow. In the slides here, you will find an example of a more complicated usage of TensorFlow. What I would recommend is that you use Keras as the interface. And I wanted to show you an example with this cancer data. So we're going to go down, scroll down a little bit here, because what comes in the beginning here is more my code for this case. But if you use the breast cancer data, I just wanted to show you an example on how you can set it up. So in this case, we don't stress with the setup of the input data. So you need to do some imports. You need to find input layers, whether it's a sequential, a dense neural network, you want to have more layers. What kind of optimizers you want to use, like stochastic gradient descent, ADAM, RMS prop, or other ADA-grad, or other types. You can specify different regularizers. You need to do, if you want to do some kind of cross entropy, you want to introduce that one, you need to introduce this categorical. So here I'm doing the plot with Seaborn. And the data set which I'm going to look at now is the breast cancer data. And in the beginning, we simply have some plotting and so on, and printing the data, just to look at the data, very similar to what we did before. But this is the way you can now set up your neural network. So I'm setting up a space of learning rates, as you see here. I just define one hyperparameter. I could define many more. I define the number of layers. I set up the number of neurons per layer. I need to have the number of epochs when I do stochastic gradient descent. I need to have the batch size when I do stochastic gradient descent. And these are all things which are fed into my neural network model. So my model is a sequential one. So this is the feed forward. I loop over the layers. I can change different activation functions. Like I can do a ReLU, I can do a sigmoid, and so on. I specify the regularizer. So I do an L2, like we did in ridge regression. Then I add this layer. So this is my final layer. So I have one hidden layer if I is equal to 1. And then I move on here, so I can keep adding the number of hidden layers. In this case, I would just have 2 hidden layers. Then I have my final output layer, which is where I have the activation function, which is a softmax. And then I define the loss function or the cost function, which is the cross entropy. I define the type of optimizer, which is my stochastic gradients. And then I define the metrics for the accuracy, and that is the accuracy function. And then I do my training, my test, and then finally I plot the data. So with Keras, this is the way you would actually set up things if you want to use Keras. So it's pretty easy to define your neural network. And we're going to see examples of this on and on for the rest of the course. And Geir is going to show you some of his notebooks, which we'll discuss today, which are more linked up with logistic regression. And if we get time, we will do some neural networks. But we will continue with this tomorrow and for the rest of next week. So because we are going to use TensorFlow together with different types of neural networks. I wanted to end the discussion about types of activation function and some kind of more critical remarks so that you can see the pros and the cons. And then we stop there for today. So the backpropagation algorithm, which we derived, that goes from, let's say, the output layer to the input layer, and it propagates the error gradient on the way. And once the algorithm has computed the gradient of the cost function with regards to each parameter, it uses these gradients to update each parameter with a gradient descent step. So the problem which has existed in the literature is actually the problem of, if you look at the sigmoid function, that can become pretty flat towards its endpoints, which means that when you calculate the derivative could end up being zero. So the derivative of the activation function enters the calculation in the gradient descent steps. And the small derivatives has often led to vanishing gradients. And that means that your training would stop somewhere in one or another hidden layer. In other cases, what can happen is that the gradients can actually explode. And then you end up with gradients which really become very, very large. And then you just get results which never converge. So what Glorieux and Benjo actually showed in 2010 in this paper was that many of these problems were actually linked up with the logistic function. And the problem with the logistic function, as we said, is that the value saturates at 0 and 1, which with a derivative which is very close to 0. So when backpropagation kicks in, it has virtually no gradient to propagate back through the network. And what little gradient exists keeps getting diluted as backpropagation progresses down through the top layers. So there's really nothing left for the lower layers. So what they showed then is to alleviate the problem. So you need the signal to flow properly in both directions. In forward direction when making predictions, and in the reverse direction when backpropagating gradients. So you don't want the signal to die out, or nor do we want it to explode and saturate. So what they did was actually to show that there are other types of activation functions, like an activation function which is called the ReLO, which does often a better job in setting up neural networks. So there's a whole family of these functions. And when you're testing a neural network algorithm, you should actually try different types of activation functions. So the question is actually which activation function should you use? So in general, it seems that this ELO activation function is better than what's called a leaky ReLO, which is normally better than the ReLO. And ReLO performs better than the TAN-H, which in terms performs better than the logistic regression. If runtime is an issue, you may opt for this leaky ReLO over the ELO function, which requires more cycles. But there you have to tweak another hyperparameter. So at the end, sometimes in the beginning, when you look at these neural networks, it's easy to get lost and don't see the wood for the trees. If we are going to summarize all the parameters, so you have the activation functions, that becomes a set of functions you need to test. You have an gradient descent method, which you can choose among as several types of methods. You have hyperparameters like the learning rate and the regularization parameters. You have the number of hidden layers as a parameter. You have the number of nodes in hidden layers as parameters. And then clearly you have the weights and the biases, which are those which define the final model for you. So when you have set up for an architecture of the network and set up the number of hidden layers and nodes and so on, that's when you train the network and get the weights and the biases, and that makes up your model. So if you look at some of the limitations on neural networks and what we have done, if you think of neural networks, the neural networks, you should not think of them as a kind of universal solution. Often you can get the same or better performance on a task can be achieved by using a few hand-engineered features. Or sometimes you may even get, if you're doing a regression problem, you may get the perfect results with linear regression or kernel regression. So if you now look at some of the problems you end up with when you do neural networks, some of the limitations, you need labeled data. And this can be a problem now when we do nuclear physics experiments, and we may have data in the terabyte or petabyte region. And that clearly, to sit there and label every event when you have terabytes of data, that means that you will need an army of people to do that. So unsupervised methods may be more relevant. However, if your data set is more limited, then these kind of supervised methods are very, very useful. In imaging, what people have been doing is actually to construct huge databases with tons of images, which are then used to pre-train networks. These typical supervised neural networks are extremely data intensive. They perform normally best when data is plentiful. And this is doubly so for supervised methods when the data must also be labeled. So that becomes really a kind of bottleneck for the usage of supervised algorithms on data from nuclear physics experiments. Sometimes, and actually this is one of the problems with basically all deep learning methods, the data are normally homogeneous. In contrast, if you, the topic which we didn't have time to discuss, like random forests or gradient boosted trees, there you can actually have mixed types of data. It's easier to implement these algorithms for that. But if you have a homogeneous set of data, then neural networks or deep learning methods work pretty well. And many problems are not about prediction. So when we do natural science, we're often interested in learning something about the underlying distribution that generates data. In this case, it's often difficult to cast these ideas in a supervised learning setting. While the problems are related, it is possible to make good predictions with a wrong model. And the model might or might not be useful for understanding the underlying science. So some of these remarks apply to neural networks, but in general, they are shared by essentially all supervised learning methods, many of these. So when we now have huge data sets, for instance, we need to think of using something like unsupervised methods, and we will talk about that next week. So I'm going to stop here with